right, 1.5 exponential functions. Let's get started. We talked about linear functions, and those are like the most basic types of functions that we can talk about. The next sort of step up would be to talk about exponential functions. So whereas linear functions, they're characterized by having a, get out of here. Hey, I need that top line. Go away. Thank you. Oh, okay, I can't point to the top line, apparently, without that bar coming down. Whereas, imagine I'm pointing at the top line, linear functions are characterized by having a constant rate of change, meaning that that ratio of change in y over change in x is always the same, right? We always add m when we increase x by 1. Exponential functions don't have a constant rate of change, but they have a constant percent rate of change, meaning that when you increase x by 1, you always multiply by some number. Or you could say you add a percent of the first number. All right, so this means that the more you have, the more you're increasing by, if it's an exponential growth, because the percent of that number is increasing, so you're increasing by more and more. It also means that if it's decreasing, then you're decreasing by less and less. So let's get familiar with the way these functions look. There are two ways to write these functions, and in this section we'll just talk about this way. This is consistent with the way we define linear functions because it explains things in terms of like how much the y value increases as we increase x by 1, like we define linear functions. So anyways, they look like p of t equals p naught times a to the t. P of t, that's like f of x, but for these functions, we, instead of saying like f of x, we usually say like p of t, because p is like the principal in like a bank account normally after t years being in the bank account or so forth. So p stands for like principal. Usually that's the name of the function. Sometimes you'll see like capital A used or something like that. Anyways, p of t equals p naught, that's this little 0 as a subscript, times a to the t. And p naught, that's like the y-intercept. It is the y-intercept. It's the value of the function when x equals 0. And a is called the growth factor. If it's exponential decay, then of course we would call it the decay factor. But it's the number that you multiply the function by for each increase of x by 1, in this case t by 1. Anyway, this is what the functions look like. They're graphs. So you can see for exponential growth, we have an increasing function, as you would expect. Something named growth should be increasing. And we have a positive function as well, right? It lies above the x-axis. And we also notice that it is concave, what is it? Concave up or concave down? Let's see. It's part of a cup shape, so it would be concave up. Yeah. All right. How about this one? Exponential decay, it looks like this. So it's decreasing, decaying. It's also positive. It lies above the y-axis. And it is concave up or down. This would be concave up or down. Let's see, this is also part of a cup shape, right? So it's also concave up. So they're both positive and concave up, but the difference is one's increasing and one's decreasing. Okay. Let's move forward. So let's see how to get that percent rate of change. So this is what the function looks like, just as a reminder. Now, you'll be asked in your problem sets to find the actual rate of change, which is a percent rate, and we'll call that the annual percent growth or decay rate. And we write the rate. We usually reserve lowercase r for that rate. All right. The factor is a, but the rate is r. All right. And you'll get some practice telling the difference between those two things. So if it seems confusing, what does a mean? What is r? What's the relationship between them? Well, that's what the homework is for. But anyway, I'll explain it here. So if you know the growth or decay factor, you can subtract 1 from that, and that will give you the rate, right? So this, remember this formula. You might write it down a couple times, see if you can memorize it. And then if we add 1 to this formula, we get this. So if we have the growth factor, we can get the rate. If we have the rate, we just add 1 and we get the growth factor. So we can go between those. All right, let's see an example. So if I want, if I have the amount, if I have a function for the amount in an account after t years, and the formula is given by this function here, p of t equals 50 times 1.07 to the t, then what rate is this growing at? So we'll use this formula here. We take the growth factor, which is 1.07 in this case, the thing in parentheses being raised to the t power. We subtract 1, we get 0.07, and we write that as a percent by moving the decimal 2 places. So 0.07, that's not 0.07%, it's 7%. And notice that 7%, that's a positive number, so this function is exponentially growing. It's increasing because we got a positive rate. Just like when you have linear functions, when the slope is positive, that means it's increasing, and when the slope is negative, that means it's decreasing. Okay, so this account started with an initial balance of 50. I know that because that's the number outside here. That's like the y-intercept. And it increased by 7% per year. All right, so that's that. And notice it's per year there because we define this as the annual percentage growth. So the next year we would expect it to grow by more, right? Because there will be more in the account. So if it grows by 7% again, well, 7% of that amount will be more than it was before. So that's how you get that shape, that exponentially growing shape. All right, but it's still growing by 7%. That percentage is fixed. Okay, let's move on. Now this is the thing we always ask you to do in math. We give you one thing and ask for another thing, and then on the next problem, we give you the second thing and ask for the first thing. So in this case, we actually give you the rate, and we want you to come up with the function p of t. All right, so it describes what's happening with this function here. It says the account started at $400 and decreased by 7% per year. So in this case, it gives us the rate. It gives us r. But in the formula, there is no r. There's only an a. So we need to use that formula that a is 1 plus r, given in the beginning. All right, so we have the initial amount. So I know that part of the formula. And then to get the growth factor, I'm just going to add 1 plus the rate. Now, it says it's decreasing, so we would count the rate as a negative number in this case. And it's decreasing by 7%. Whenever we do calculations, we almost always change the percent to a decimal. So we write negative 0.07. So 1 plus a negative 0.07, that's 1 minus 0.07, which is 0.93. So this is the decay factor. This is the decay factor. This is the decay factor. This is the decay rate. This is the decay rate. This is the decay factor. Those two things are related by this formula, a equals 1 plus r, but they mean different things. One we use for our formula, and one we use to understand, to kind of conceptualize the function. All right, so here's the function. That's it. And just as a note, just to make sure that you don't try to do this, this is as simple as we can write the formula. Okay, we cannot combine 400 and 0.93. We cannot multiply those two together to get 372 to the t. No, we can't do that. One reason is that you remember order operations. The exponent comes before multiplication. So this is as simple as you can write it. All right. We like to try to oversimplify things. Our brains do, but sometimes it's as simple as we can make it. All right, so that's that. Here's a little graph of the function. Starts at 400, goes down by 7% per year. Notice it's going down by less and less. Since it's decreasing, 7% of a lower number will be less, so it will go down less each time. Okay, goes down by less and less. And it never actually reaches zero. It never actually reaches zero. It just keeps going down by a percent of what you have. And so there will always be some left, but it will get very close to zero very quickly. All right, that's that. Let's move on. Let's look at another set of things to keep in mind. So on the first example that we saw, we had an increase of 7% per year, meaning that R was positive 0.07. And when we found the formula, our growth factor was 1.07. And on the second example, we had a decrease of 7% per year, so that rate was negative 0.07. And so 1 plus a negative, that was the number 0.93. So this was the formula we came up with. So keep in mind, what we notice here is that when we're multiplying by a number bigger than 1, that's going to correspond to an increasing function, right? If you multiply a number by something bigger than 1, that's going to increase that number. And when we multiply by a number smaller than 1, that's going to decrease the number. So that's going to be decay, because this is less than 1. This is growth because this is greater than 1. Has nothing to do with this initial amount, whether it's increasing or decreasing. Okay. And another thing to note is that the time it takes to change by any fixed percentage is constant. So these functions were increasing at a rate of 7% per year or decreasing at 7% per year. But we could also consider how long it would take this function to, say, double. And that would be called the doubling time. That time it takes for the function to double would be called the doubling time, and that would be the same no matter what amount you start with. If you start with 50 and go to 100, it would take the same length of time, meaning the same distance on the x-axis, to go from 100 to 200, and from 200 to 400, and so forth. That distance that you need to travel in the x direction, it's the same. And for decay, it's the same thing. For the amount of time it takes to decrease by, say, 50%, so that would be called the half-life. It would be half of what you started with, is the same. So I don't have another slide for this, but hopefully you can just try to listen and understand that the amount of time it takes to go from 400 down to 200 would be the same length of time that it takes to go from 200 to 100, and then from 100 to 50, and so forth. The x direction, the x distance would be the same. Okay, so I'm not sure that that's going to come up for us, but it is something to keep in mind. All right, let's move on. And I have one more example here for you. So let's suppose that we're running a business and the number of customers fell from 2,329 to 1,899 over the last 6 years. And we have a question here: what is the percentage change per year? All right, so it tells us, it doesn't seem like it gives us enough information in the beginning. We only have two y values. These are values of the function, and we have the change in x between those two y values. And let's be clear on what we're being asked here. We're asked for the percentage change per year. Well, remember what that is. That's R. That's the rate. That's the rate expressed as a percentage. Okay, that's the annual percentage rate. That's R. So we want to find R. And we know that we have a formula that gives us R when we have A. R equals A minus 1. And we also know that this is the initial value of the function. So let's write that down. So what I like to do for many math problems is to first just write what your equation looks like. All right, our function looks like p naught times a to the t. Get used to writing exponential equations like that. And I can go ahead and put p naught in because that's the initial value of the function and it tells me that. So I'm thinking of t as being t years after this point at which we have this many customers. And then times a to the t. And we'd like to find a. And you remember back from when we did linear functions, if you want to find, say, for example, the y-intercept, but we know the slope, then we can plug in an xy coordinate and solve for that y-intercept. And we're going to do a very similar thing right here. So I will plug in this point here. I know that after 6 years, the number of customers is 1,899. So I will plug in 1,899 for the y value, and I will plug in 6 for the value of t, and I get an equation with only one variable here, which I can solve for. So let's see how we do that. So first I'm going to divide by 2329, and I'm going to get this. And then I have this number equals a to the 6th. I don't want to divide by 6 or anything like that. What I want to do is take the 6th root of both sides. So just like a problem that we've seen before, whenever you have like x squared equals something, you can take the square root to solve for x. Whenever you have something to the 6th power, you can take the 6th root. That means taking it to the power of 1/6. So I'll take that, and I'll make sure to put parentheses around everything when I do my calculation. Like I'll put parentheses around my 1/6 in the calculator as well. And what I get is 0.9666 when I round to 4 decimal places. That's the growth factor. All right, almost done. Once we have our growth factor, we can subtract 1 from that and get our rate, get our percentage rate of change. And when I subtract 1, I get minus 0.0334. And after I move the decimal 2 places to write that as a percent, it is minus 3.34%. And since it's an annual percent rate of change, I will put percent per year. So I'll write that as my units. Okay. So just to sum up, because there was kind of a lot happening on this slide, and you might be tempted to go in a different direction than I did here. So I'll try to point out why I did what I did. First of all, what I did was very concrete. I just wrote the form of my function, and I filled in what I knew, and then I plugged in an xy coordinate. This coordinate here that was given after 6 years, the function was 1899, and I reduced my function to just an equation with one variable, and then I just solved that. So what I did was very concrete. You might be tempted to think about this conceptually and try to answer it that way, but try to figure out what's going on and make some observations and go from there. And sometimes that'll work for problems, but it might not help you in this case. I think this process needs to be done. So for example, well, before I say that, I want to point out here, notice that when we took the 6th root of both sides, normally when you take the square root or the 4th root or the 6th, some even power root, then you need to write a plus and a minus. So if while I was talking about this, if you're wondering about that, why didn't we put plus or minus? Well then, technically that's true. That would also be a solution, but that wouldn't make sense. The minus wouldn't make sense in this situation because then we would have a negative growth factor, which we can't have a negative growth factor. We'll always have a positive growth factor, or decay factor. Now, if it's a decay factor, it will be less than 1, but it will still be positive. So we'll always end up with a positive number. So when you're taking roots and things, you only need to write the positive one for these exponential functions. So that's the first thing. Now, in terms of approaching this problem, you could calculate the relative change from 2329 to 1899, like we did, I think, in section 1.3 maybe. There was a section on average rate of change and relative change. So that would give you the percent that it changed from 2329 to 1899. Remember how that works? You take the difference in the y values and you divide by the initial y value. That'll give you the percent that it changed from 2329 to 1899. Then you might be tempted to just divide that by 6, since the percent change divided over 6 years seems like it should give you the percent per year. But that's not going to work here, because even though it is changing by a constant percent, if something changes, let's say 50% over 2 years, that doesn't mean that it's changing, decreasing by 25% over the first year and 25% over the second year, because after the first year you have a different amount, so that percentage of that amount will be different. So it's a little bit hard to explain, but you kind of need to just work problems and you get an intuition for how this stuff works. But the big point here is that thinking about it like that won't land you the right answer in this situation. So I gave you a very concrete way to solve problems like this that you'll see on the homework. So I hope that some of that made sense, at least, and if it didn't, well, that's what the homework is for. And of course, you're always free to email me, come to office hours, ask questions like that, and I'm happy to try to clear up anything the best I can. All right, that is all for now. Have a good day and good luck with your stuff. All right, goodbye.